So, ladies and gentlemen, welcome to the International Prague seminar on function spaces. Our today's speaker is Bogdan Raita. Hopefully, I'm not mispronouncing it too badly.
Perfect.
And his topic is the compensated compactness method for concentration effects in nonlinear function spaces, I believe. So the stage is yours.
Thank you very much. It's a real pleasure to be here and for the opportunity to present this work, which is joined with Andre Guerra and Matthew Schrecker, whom I think are in the audience as well. So I got my back covered on this in case there's any tough questions. So let me dive into the topic by presenting an old kind of like Tartar's dream from the mid-70s concerning universal models for continuum mechanics. So what Tartar said is, say we can express a nonlinear PDE as a coupling between a linear PDE, which is represented here by an operator A, which carries all the differential structure of the problem, and a nonlinear pointwise relation without derivatives. The first it's called balance relation, and the second is constitutive relation. And let's say we also have some sort of approximate sequence of solutions. This could be like some minimizing sequence or some regularization or so on or so forth, singular perturbation, you name it. And let's say you have some weak compactness principle that tells you the approximate solutions are converging weakly, are stable under the linear relation and the pointwise relation, and you're inquiring when can I pass to the limit so that I can conclude that V is a solution of my PDE. So it's a fairly abstract model which has been studied. And many models have been incorporated in this. In particular, I would stress out nonlinear elasticity and let's say the Euler equations. Okay, so from this point of view, let me cite a very old theorem due to Vitali, which is saying that the strong convergence that we're looking for is equivalent with kind of like convergence in measure or pointwise, let's say absence of oscillation effects. And if you're converging strongly in LQ, also Q uniform integrability. So a quantified property that's stronger than the boundedness in LQ. And these two phenomena are by Vitali's theorem the only ones which might cause disruption for the strong convergence. So failure of oscillations or emergence of oscillations or emergence of concentrations. I'll also, for presentation purposes, write down two very simple examples that everyone must have seen in analysis at some point. Let's take a simple periodic oscillation, let's say sine of Jx. This will converge weakly on average to 0. But it's definitely not converging pointwise or in measure. It's fast oscillating. And let me also display a one-dimensional LQ concentration function, just the right weight to a shrinking interval. From this point of view, let me briefly interrupt my presentation of Tartar's framework with kind of like a recent development that I proved jointly with Jan Christensen. This is more kind of like, let's say, for marketing purposes. So what is known kind of like in this framework, let's say without pointwise constraints, is that if you look at convergence of gradients in Sobolev space, you can actually prove powerful decomposition lemmas to show that oscillation and concentration effects separate. And what has been known for a very long time is that in p equal 1 this is no longer the case, and because the oscillation effects, and here I mean oscillation effects in the sense of Young measures. So the oscillation and concentration effects can be quantified by using generalized Young measures, which I will not discuss here. But basically what happens with P equal 1, that any L1 oscillation Young measure can be generated by a sequence of weakly convergent gradients of BV maps. And the thing that we realized very, very recently is that quite surprisingly, the concentration effects do indeed have gradient structure. So the split between oscillation and concentration effect is completely nonlinear. In P1, this is not true for P between 1 and infinity. And we're now working to understand this kind of like surprising phenomenon better. But anyway, this was my short commercial break. Let me carry on with Tartar's framework in more detail. So let's rule out oscillations. This is let's rule out concentrations. Let's say we're looking at a weakly convergent sequence of approximate solutions in L infinity. This is kind of like standard for like gradients of Lipschitz mappings that were studied in nonlinear elasticity. And we're looking at a compact set of constraints. This has been studied for the past decades by many outstanding researchers with absolutely remarkable contributions. One other example, as I was saying, is the Euler equations as formulated by Camillo De Lellis and Laszlo Cecchini. They can also be put in this framework. And I think there's very recent work to understand concentration effects in that direction too, but I'm not so up to date. What we looked at, and we would like to propose for a more general study. There have been several examples, but the mindset that we took was to say, okay, let's forget about specific examples or instances of compensated compactness. Let's say we will not inquire about oscillation effects. We'll allow them to simply exist. Let's say they can be separated from the problem by some sort of truncation or whatnot. We will only look at concentration effects. So we'll take a bounded sequence in an LQ space, satisfying a constraint in LP, so both quantified separately, and we'll take a pointwise constraint, which of course allows for like large values. So this set C is essentially a cone. It's allowed to go out to infinity in every direction. And the question is, can we turn LQ boundedness into Q uniform integrability? Let me give you an example of when this can occur. So this would be the theory of quasi-regular mappings of bounded distortion. Let's say we're looking at gradients du. So in the Tartar framework, they would satisfy the linear PDE. The differential structure would be curl-free sequences of gradients. And the cone of admissible values, it's the kind of like cones of distortion kappa, where we're basically allowing for maps that don't distort volume too much when compared to kind of like, let's say, Frobenius norm or something. And basically the result I'm thinking about in connection to uniform integrability is Müller. I think Stefan Müller's first result was to prove that if you start with a sequence of gradients of quasi-regular mappings that are bounded in Ln in n-dimensional space, then there's an additional cancellation property of the determinant actually, which lets you prove that the sequence is actually bounded in Ln log L, and therefore, independent of the bound on the distortion, you show that Ln boundedness can be automatically improved to n uniform integrability. And indeed, you don't even need to start with Ln on the right hand side here, at least if you assume have a sequence of homomorphisms. if you have like quasi-conformal mappings, the original inequality of getting is can be stated as the reverse Holder inequality ln L1. So in particular, if you only take a sequence of gradients that's bounded in L1, then you can conclude n uniform integrability, which I think it's quite remarkable. And of course, there has been like extensive studies of these higher integrability and the ellipticity phenomena in geometric function theory. In connection with this or this sort of inequality, we look at, let's say, Sobolev-like or seemingly Sobolev-like inequalities of the form V in LQ can be controlled by the linear differential operator coupled with a nonlinear constraint V equals C. So let me display our object of study again. So they really look, they're nonlinear higher integrability estimates resembling the Sobolev inequality, if you wish. However, the competitor maps are only allowed to take values in a set of in a cone C. So of course, let me start with kind of like the trivial example for this. When you have a so-called elliptic operator on the right-hand side, or if you want injectively elliptic, if you can more or less invert the operator A in Fourier space, then you're in the solution of looking at the Sobolev inequality. So here you can just you can reduce the whole estimate to the Sobolev inequality, and you don't need to take any sort of constraint. You can just allow for the full vector space on the right. It's a linear estimate. Let me highlight the fact that P star L will mean the Sobolev exponent for some sort of higher order operator. Right here I take an nth order operator and I get some different expression. Okay, but this is just a technicality. P stars will always denote Sobolev exponent. Okay, but this is a completely uninteresting situation for us. We just have if you have ellipticity, then you don't care about the nonlinear constraint. This is kind of like the trivial case for our theory. What happens in for non-elliptic operators, so in particular, if you have a direction in which the operator is not invertible in Fourier space, say this direction here Z, for which there's a frequency psi such that a psi of Z equals 0, then you can construct plane waves in direction psi with amplitude Z. And of course, the plane wave, the shape of the plane wave is arbitrary, so you can basically construct arbitrarily bad examples for this inequality. Therefore, we get kind of like an immediate necessary condition that if we allow for ellipticity to fail, as we should, then we must rule out these directions of non-ellipticity from the nonlinear set. So we always have cone intersect set of bad directions has to be trivial. Okay, so now we can start thinking about estimates that depend on both operator and cone C, and I'll give another very simple case, which is still the linear case. I take a linear space which intersects the cone of bad directions, or I'll call it set, even though this is also a cone. I'll call it the bad set or set of bad directions. It's the wave cone in Tartar's terminology, the wave cone of the operator A. This intersection here has to be, if the intersection is trivial, then you can reduce again to the Sobolev inequality. Okay, not very surprising. Still linear case. And the only result that I know of that extends this in generality, so meaning for each operator A, is a result by a team of five people. I do not manage to include all their names in the slide, so I'll just read them out. Where these are Adolfo Arroyo Rabasa, Guido De Filippis, Jonas Hirsch, Philip Rindler, and Anna Skorobogatova. They very recently proved in the limit case P equals 1, they showed that if I take any operator and any linear space that intersects that does not that intersects the wave cone, the bad set trivially, then there exists a small enough cone of values in a neighborhood of this linear space, so kind of like a perturbation of the previous result, such that the subcritical LQ below Sobolev exponent, LQ L1 inequality holds. So in particular, it looks reasonably similar to the kind of like linear theory, if you wish. So the linear theory can be perturbed. This is what they show, and moreover, they conjecture the following: motivated by some examples that suggest that convexity in the set of directions is important. They conjecture that if you take a closed convex cone of values that does not intersect the bad set, then you have then the subcritical Sobolev exponent with p equal 1 on the right should hold. And this is quite surprisingly checked for one example, for one pair, when you have divergence on the right hand side and the cone is contained in symmetric positive definite matrices, so kind of like a subcone of positive definite matrices. Then Denis Ser showed quite recently that the actual Sobolev, or like Gallardo-Nirenberg Sobolev inequality, if you wish, V in L1 star is controlled by the divergence in L1. This is a very non-trivial and very surprising inequality that was very important, a very important starting point for our work. And okay, so both of these are examples with p, or I mean the conjecture and the example are with p equal 1. So is it special in any way? And again, very interestingly, there's an example by Antonio De Rosa and Riccardo Tione, which says that, okay, so if you take p bigger than 1 on the right hand side and the same kind of cones, then you cannot, there's counterexamples to show that you cannot take q bigger than 1 star on the left. So this definitely seems to suggest that the theory altogether is different than linear theory, for sure. And it seems to be that p equals 1 is important, as well as the Sobolev exponent on the left is important. And these are the questions that we tried to address. And actually, it turns out that the answers are no, it doesn't. It's not directly related to p equal 1. And no, it's not really about the Sobolev exponent on the left. So what do I mean by this? Let me present a couple of our results. So first, let me make a small disclaimer here that the cones that I'm citing will be not so transparent. They have slightly complicated definition, and I will present it later on in the talk. But the point is the following: for the curl operator on the right, we can find an indexed family of cones, like integer indexed family of cones, such that we get subcritical Sobolev inequalities of the form V in LK is less than curl in LP when P is when K is slightly below the Sobolev exponent. And these are and these examples are kind of like optimal in the sense that they cannot be you cannot take a higher exponent than K on the left. So I'll go into this in more detail later. So we have a kind of like interesting family of inequalities for curl on the right, with surprising and geometric cones CK that I will define later. And there's a corresponding dual result for the divergence operator, which says that, okay, you can take a related family of cones CK tilde, so that another index family of exponents is relevant. It's kind of like optimal on the left hand side. So it really seems that it's kind of like it's about div, it's about the cones in particular, and it's about it's about some fixed exponents on the left, not really the Sobolev exponent, although there is a relation. Okay, so let me try to say one consequence of this result, which is that in particular, if you take a modification of this example that allows for curl-free fields, so for gradients, we obtain reverse Holder inequalities which are completely reminiscent of Gering's. So in particular, if we take curl-free fields in our cone CK, we get an inequality like Gering's. Gering has covers kind of like the endpoint k equal n, and we have a corresponding result for divergence. In particular, what do we learn from this? We can say that because of course, as we know, reverse Holder inequalities are self-improving, we can infer even higher integrability results, which I will just refrain to uniform integrability, and let me state the result clearly. Let me say we have a sequence Vj of gradients that are valued in one of these special cones Ck and are uniformly bounded in L1. Then the sequence of gradients is locally K uniformly integrable. And again, this K is kind of like a sharp, it's like a sharp power. You cannot given epsilon, we cannot infer the boundedness in Lk plus epsilon. So the results are very sharp, and indeed, it would be amazing for analysis if we would have a theory that explains these examples, because of course, what we show and what is our major achievement here is that we can look at the geometry of the nonlinear cone CK, couple it with the linear differential equation, and infer a kind of like quantified pure analysis property. It would be really, really great to have an algorithm that, given a cone and an operator, can you say what the correct exponent here is. So let me say a bit more about this. First of all, let me say, okay, so we've kind of shown. Let me recall the conjecture from the 5 people. It's basically saying that whenever you have a convex cone C for admissible values, then you always have subcritical Sobolev inequalities with p equals 1 on the right. Okay, so what we showed with these kind of with our examples, we showed that, well, if you have p on the right, then it's not really about the Sobolev example. This we showed, and let me explain that you can also take p equal 1 on the right, thereby disproving their expectation. So let me construct in 2 space dimensions. And I now realize this k equals 2 comes from a previous iteration of the slides. This should be just in 2 dimensions. Let me take a cone in the. There exists a cone in the interior of symmetric positive definite matrices, which is in L2 but no better. Or it's in L2, but it's not in L2 plus epsilon, though of course there's probably some bare category argument to show that you can do L2 and no better. In any case, how can you construct such a map? You would take some sort of the rotated gradient of a radial map, or Hessian rather. And what do we do with this? Well, we say, okay, if this map is divergence free, then it's also divergence squared free, where perhaps I should clarify that divergence squared here is kind of like an abusive notation. It's basically saying divergence of a vector field applied to the divergence of a matrix. So if you take this this operator, do a simple cutoff, and mollify, you then obtain a sequence that's in that for the Sobolev-like inequalities, you can take L1 on the right, but you cannot take any better than L2 on the left. This is a simple technicality, whereas their conjecture would imply that you're allowed to go all the way up to the Sobolev exponent, but if you take div squared, so a second order operator in dimension 2, the Sobolev exponent is infinity, so of course it's ruled out. In particular, yeah, basically the limit exponent here is 2, whereas they would predict you can take anything. Okay, so this is actually quite a simple way to disprove their expectation. So the question is, what can we do instead? How can we improve the theory? And our expectation can be briefly formulated along the following kind of lines. If you would kind of like ignore the technicality revolving around these kind of like open and closed cones, we can explain this quite simply in the following way. Given kind of like a fixed cone of values for the pointwise restrictions and a linear operator A, an inequality LQ LP holds. For Q, it always has to be below the Sobolev exponent, but also below a certain threshold Q max, which we called Q max. Sorry, I'm about to kind of sneeze. Q below Q max, and this Q max should depend only on the operator and the cone. And of course, it should be optimal in the sense that if you take any value above Q max, you cannot have any sort of inequality like this. This is our expectation. If we are to compare it with Gering's old inequality from 73, we'd expect, for instance, that this for quasi-regular mappings where you have reverse Holder inequality ln L1, you expect the Q max to be exactly n. And of course, there they only have quasi-regular cones, but we actually checked it for, at least in 2 dimensions, we checked it for cones that have kind of like completely arbitrary signatures. Okay, so once again, what we're saying is that if you have a Sobolev inequality of this, if you have a nonlinear inequality of this type, it always has to scale at least like the Sobolev inequality. So the Q on the left has to be below the Sobolev exponent. Okay, that's pretty clear. But on the other hand, we say that whenever you have kind of like reverse Holder inequality, I mean, what we expect, and we checked in some examples, we expect that whenever you have reverse Holder inequalities for exactly A free fields, then you must be below a certain value Q max, which depends only on the cone and the operator, and not on the P on the right hand side. Okay, so I will briefly show an example today where we checked our conjecture completely, and let me also say that the examples for div and curl that I presented above are partial results for our conjecture, so they're consistent, of course. We have such results for 2x2 matrices or symmetric matrices. We also have more exotic operators, such as this would be div squared minus Laplacian composed with trace. This is actually a kind of like a, let's say, kind of canonical alternating operator, although it doesn't look it looks fairly non-standard. And we also have a kind of like a div curl operator, which we constructed completely algebraically, or we recovered completely algebraically, and for which we have similar results consistent with our conjecture. Okay, so let me look at the time, and how much time would I have in total? Would it be like 45, 50?
We are not fussy here. More, just take it.
Okay. I expect I would finish in roughly 20 minutes, let's say. Thank you very much.
That's fine. It's fine. Whatever.
Okay, so what we did is we found a connection between a family of cones, which I'm again signaling in red because they're not defined yet, but these cones I will define explicitly very soon. There's a family of cones indexed by k, such that for the divergence squared operator, we have a second order Sobolev inequality up to a threshold k over k minus 1. We can kind of like, and a similar related subcritical result for p equal 1. So this I will go over in some detail. We also can show that for our example, the Qmax value, the maximum integrability on the left hand side is this number k over k minus 1, and similar problems emerging in different contexts in geometric function theory are really hard problems, and it's not. It's sort of, we're very happy that we found a family of examples where we can compute it. Okay, so furthermore, yes, so I will only focus on the first part with p bigger than 1. The other one has the same kind of proof, and I will sketch a proof quite in some detail. And the interesting connection that we observed is that you can prove this Sobolev-like inequality by duality with the so-called K-Hessian equations, which are nonlinear elliptic equations, and which are defined in the following way. They're defined as Fk is a function of symmetric matrices M, and it's the kth symmetric sum of the eigenvalues. So you take the kth symmetric sum of the eigenvalues of the Hessian, and of an unknown function u, you put a positive f on the right hand side, and you can determine u, let's say. So for example, when you take just the first symmetric sum, this is just the sum of the eigenvalues, it's the trace. So you take trace of the Hessian, this gives you the Laplace operator, and the equation is Poisson's equation. If you take the nth, the nth symmetric sum of these n eigenvalues, this will just be the product, and of course the product of the eigenvalues is the determinant. The determinant of the Hessian gives us the Monge-Ampère equation. So these are kind of like if you wish, K-Hessian equations would be an interpolation between the linear Poisson equation and the famous Monge-Ampère equation. So okay, why are these equations special? They are, well, first of all, fully nonlinear, autonomous, elliptic, and what's, as I write here, nasty about them is that they're degenerate. And moreover, so the way in which many difficulties are overcome for the endpoint n of the Monge-Ampère equations, the connections with optimal transport, these are not present for k lower than n. So okay, let me go in a bit more depth about these equations. So if for Monge-Ampère equation, usually you're looking at convex solutions. Here the admissible, the kind of like domain of definition for the admissible values is the gamma k cones, which are defined as the first k symmetric sums of the eigenvalues of a symmetric matrix are positive. So in particular, of course, when all of them are positive, when you're looking at the Kn cone, you get all symmetric positive matrices. This corresponds, if you have Hessian is in symmetric positive definite, then you have a convex function. And at the other endpoint, gamma 1, when you have just the first symmetric sum is positive, then you just have traces positive. So we'd be looking at superharmonic functions or subharmonic, same thing. The other object that we'll be looking at is, okay, so Fk being a sum of products of k values, it's a k homogeneous function. And in particular, we will rescale it. It's very convenient to rescale it to make it one homogeneous. And this function here is concave in the domain of definition gamma k. This is an important property, I guess, first proved by but I'm not.
Sorry to interrupt you. You have some issue with your microphone. It sounds like a loose contact or something.
Oh, okay. I'm not really sure. Is it okay if I stand closer to the?
Oh, it sounds like your mic was partially unconnecting or something like that.
Okay.
Yeah, but it only happens from time to time, so maybe you can continue. Maybe it will be better now if you try to change something.
Okay. Please let me know if there's any problem. I also have another microphone that I can use.
Okay. At the moment it's okay, so hopefully it will
Okay.
stay
So
like that.
if it I apologize for this. If it happens, I can get the other one very quickly. Okay. So rho k will be our one homogeneous substitute for Fk. Okay. So from this point of view, I really prefer to write the k Hessian equations as rho k of Hessian equals F. The reason being that, like linear differential operators, they would be one homogeneous. The operators on the left. So here for this sort of equations, there's really satisfactory existence theory and kind of like basic estimates, and this was done by Trudinger and then his collaborators, and I guess for Monge uniformly elliptic equations, there's a lot of inspiration from the works of Caffarelli and his co-authors.
Okay, so sorry, it's happening again. Maybe if you could switch the mic.
Sure. Give us a couple of minutes. Okay, thank you. So now maybe the break was not so disruptive, because now I can come back to this full slide and say and highlight two important aspects, namely one that, so looking at this equation, there's two things that I really want to say. One, that you don't expect convex solutions. You just look for solutions with Hessian in these gamma k cones, which definitely allow for negative eigenvalues or change of signs between of the determinant and so on. And so no convexity. And also there's a very important fact that even to define weak solutions, you need the right-hand side to obey at least LK integrability. So this will be, I guess, ln for Monge-Ampère. There's you need at least this much, and this will be absolutely crucial in the sequel. So let me try to carry on. The basic LP estimates that we're going to use are estimates of Trudinger, which are basically saying that as long as you start with the at least right-hand side and at least LK, then you have exactly Sobolev estimates for the second order Sobolev estimates for the solution. The solution to the Dirichlet problem. And this we're going to use. Let me highlight that this is already very non-trivial. if for no other reason, at least for the fact that you have the sort of barrier that depends on the geometry of the cones gamma k, and by contrast, if you would just try to look for du in r star here, so a Sobolev estimate, an estimate on the gradient, these are completely open. I think, except of course except Monge-Ampere, but I think it's fair to say, and please correct me if I'm wrong, but I think they're really completely open. So it's really a kind of like still young and kind of like difficult theory to look into, and the limitation that you have to have at least right hand side and at least LK is related to the loss of ellipticity, to the way in which this the nonlinearity degenerates, the ellipticity of the nonlinearity degenerates. Okay, and now I will define the dual cones gamma k. These are dual cones in the sense of convex analysis, so nothing very fancy. What's more interesting, and of course they're kind of like, at least in theory, they should be computable. The interesting objects, I will also define dual nonlinear one homogeneous function. So think of this as kind of like a Legendre transform, or like like a convex conjugate, but for one homogeneous functions. So it's kind of like it behaves very well, and by the very definition of comparing rho k via inner product with rho k star, you have that sort of I guess an analog of the, I'm not sure exactly what's the name of it. I think it's like Legendre-Fenchel inequality. I mean, it's let's say going in this direction. So rho k times rho k star is bounded by the inner product of the two matrices A and B, as long as A is in the cone gamma k and B is in gamma k star. This is kind of like the crucial property that will allow us to pass from nonlinear equations to kind of like linear looking estimates. Okay, so how are we kind of like put together some ingredients. Here is where we use the gamma k cones, trying to estimate the norm of V in some LQ space. We will compare the norm of V in LQ with the one homogeneous quantity rho k star of V. This is more or less by definition. So we only look at cones that are contained there. It's kind of like how we measure the ellipticity in some sense. We stay a bit away from the boundary of gamma k star, and therefore we have control of the norm by this quantity, one homogeneous quantity rho k star of V. And then we rewrite this power here. We rewrite it as a product between rho k star and rho k of unknown function. This is the auxiliary equation written below. I will of course use estimates on U. But to carry on, the product rho k star rho k we estimate by the bilinear inequality that I just stated here. So we kind of like now we're kind of like in a linear realm where we can integrate by parts twice. And you can also take this as a definition of the operator divergence squared, sorry. We would be in this position. Integral V to the Q is less than integral U, auxiliary function, div squared V. Div squared V we have. Let's try to see what we can say about U. U has an estimate that we know. It's kind of like the second Sobolev estimate of this type, where on the right hand side, I also use the fact that rho k star is one homogeneous and continuous. So of course we can do some very nice computation with exponents, which for me at least it takes like a statistically unlikely number of tries to get it right. But we can kind of like register what do we want this R to be given P on the right hand side. What do I mean by this? I mean that in the next step, we will take div squared v to be in LP. So we'll do just the Holder inequality here. LP prime LP, like so. So in particular, we take the correct kind of estimate for U. We make we get the computations right. And in the end, we should obtain exactly this quantity here, which gives you an exactly second Sobolev inequality. But let's not forget that there's an important restriction here when we take R has to be at least K. So this R at least K gives us the fact that the exponent on the left hand side has to be at most K over K minus 1. And of course, let me iterate this. Let me say again, K over K minus 1 here is not an artifact of the proof that we tried by duality and we got this, so this is what we have. No, it's really, we can construct examples similar to the one I mentioned of De Rosa and Tione, and we would have any LP bigger than a certain value. If you increase it, you cannot exceed K over K minus 1 on the left. So it's really, really sharp, and it's really that the geometry of these cones and the degeneracy of the K Hessian equations really, and of course the bounds that we use in the middle, all of this goes through, and it's kind of like it's carried to the very end to obtain an optimal exponent on the left. So it's phenomenological. It's not because of the method. And let me also highlight that actually the proof I wrote is not just bounding the norm of V in LQ, but really the quantity rho K star. So here I'm displaying a slightly stronger inequality, which involves a quantity on the left that degenerates. So this rho K star degenerates in the same way in which the cone, kind of like respecting the geometry of the cone in a way that we can allow for all values, not just as I write here, C be a closed cone contained in the interior of gamma K star. This is the variant of the estimate that kind of like respects the cone and the so what I'm trying to say here, and I'm not doing a very good job, is that this cone rho K star, this kind of like mysterious cone rho K star, it contains forbidden kind of like bad directions in its boundary. And even though we lose ellipticity in those directions, it's really important and quite fascinating that we get the right quantity on the left that degenerates in such a way that where we lose ellipticity, we take kind of like the right scaling, if we wish, so that we don't lose the estimate. So I will actually, the intermezzo I had in mind here will be a finale, because I don't want to overrun too much. Let me say another word about the quantities rho K star, and namely that the crucial quantity rho K star lifted to the crucial power K over K minus 1 gives you, surprisingly, a divergence quasi-convex integrand. So what does this mean? And kind of like by definition, it means that we obtain the reverse Holder inequality that is written here. Reverse like Holder inequality that is written here for periodic fields, divergence-free periodic fields, even divergence squared, but this is more or less a technicality. And of course, it's nice because we have the precise constant 1, and of course it might play an important role for kind of like applications to lower semi-continuity and minimization. And let me also mention that Denisser first proved this in the case K equal N, but there he only had like determinant appearing and not the row k functions. Had I gone on, I would have said that we can look back at the cones gamma k and kind of like say that, let's perhaps spend half a minute on this result here, saying that, okay, so how do we generalize both kind of Müller and Gering's examples? Well, we generalize them by looking at cones, at special cones inside gamma k. So in particular, we're not looking at sort of like quasi-regular mappings theory. We allow for kind of like degeneracy in the gradients. We obtain the same sort of higher integrability estimates with a different power, not ln log L, but lk log L, which respects the geometry of these new cones, which are kind of worse, if you wish. They contain more degenerate matrices. And not only do we get the same kind of inequality, but actually it holds with curl on the right hand side. So it's kind of like directly perturbed, if you wish. So because I talked a lot, and there was also the interruption, let me give a very, very brief summary of what I said so far. So we look at Sobolev-like inequalities of this form with a differential operator on the right, and kind of like in principle convex constraints on the test field. These are inspired by the study of certain concentration phenomena, and we disprove the kind of like naive expectation that the behavior is like for Sobolev inequalities. It's not. The exponent on the left, it depends on A and C, but not directly on P. And this is exactly the conjecture we propose, and it seems that it's very difficult to compute this maximum higher integrability that we can allow on the left. We check it completely for the div squared example in the cones gamma k star that I presented earlier. And we give other cone operator examples of cone operator pairs for which we check various regimes. And of course, the last thing I mentioned is that these generalize the geometric inequalities of Gehring and Müller. We kind of put them in a framework where it's like, let's say slightly more PDE, slightly less geometry. And of course, let me conclude with a naive remark, which is probably best describes the kind of like summarizes the summary, if you wish. And the remark is that the trying to do a study that kind of like given A and C spits out Q max seems to be a very, very hard problem. So thank you again for the invitation and for the attention.
Okay, thank you for the interesting talk. Let us thank the speaker, please.
Thank you.
Okay, are there any questions?
I would have one if I'm allowed to.
Of course.
Please.
Bogdan, thank you for the beautiful talk. I think this, as far as I can say, I think these are beautiful results. It's sort of too many of them for me to comprehend. Some questions I would have probably very naive, but you mentioned several times this optimal, how you call it, exponent, like this Q and things and K, and at several occasions, especially in connection with this Miller's result, you mentioned some special Orlich spaces as well. I mean, natural question is there any hope for any improvement? If there is no improvement in Lebesgue spaces, is there perhaps any hope for improvement in Orlich spaces, or is it too difficult? I mean, I have no doubt that the study is very hard, as you say. So But anyway, I mean, this is a natural question. Maybe it's too difficult to study in that context. I don't know.
I think so. This pertains more to the other project with Andre Guerra and Matthew Schrecker, where we the ln log L, or so let's just turn to this last slide here. So in particular, this inequality, right?
Right.
The log L comes from a local Hardy space bound. So it really it comes from the kind of like sharp statement would be that rho k of v is in local Hardy space when it's positive. And I think this does not really go into, so it will embed wherever the local Hardy space embeds into. And this I don't know. This the experts must be in the audience. But this is the answer, and I think you cannot do better than so instead of LK log K, put a K homogeneous quantity on V, which is like for Müller's result, it would be determinant of the Jacobian is in local Hardy.
Mm-hmm.
And that is probably the best space.
So it goes back to the embeddings of the local Hardy spaces.
Exactly.
Good. Okay, thank you very much. Good to know.
Sure. But indeed, the logarithmic improvement comes from our paper from 2020.
Okay.
Yeah.
Are there further questions? Okay, probably there are no further questions. So let us.
Maybe I can have one more.
Okay, of course, Lubos.
This thing at the beginning, Bogdan, that you mentioned with this cancellation property. I mean, that was when this du goes to du in NL. Yeah, this one here. And then you said something about this n uniform integrability. Is that some kind of a Valais-Poussin behind that, or?
Yes. The jump between the log and the extra log gives, yeah, of course.
Right. Okay.
Yes. It's self-contained. I mean, this is the. If you believe the inequality, then the uniform integrability follows by the Valais-Poussin.
Yeah. I like it. I believe it. It's optimistic. My last remark, perhaps, I like this musical terminology that you keep on using. Are you a musician in some way, or?
No, actually, I am not. What is
There was some intermezzo, finale, things like that.
No. It was just. It so happened that that there was the change of schedule.
Okay, so my final remark is you are always welcome in Prague, also in presence. So whenever you feel like visiting us, just let us know.
Thank you. That would be my great pleasure. It's a beautiful city and extremely nice people. So I'd be very happy to keep in touch about that.
All right. So if there are no further questions, let us thank the speaker again.